Hey everybody, what's going on? So in this video we're going to dive into an epicyclic gear dynamics problem. As we see right here we have the epicyclic model. What we have right here, they're calling gear a sun gear. Okay, and it's fixed about this point right here. It's fixed about that point. It could rotate, it can't translate. Uh, And then it's also in mesh with planet gear B. In mesh just means that they're in contact. So this is planet gear B, okay, outside, and we see it's concentric with this gear C. And they mention it right here. They say that planet gear B has an inner hub C, okay, that's fixed to B, and in mesh with the fixed ring gear R. So if we zoom in right here, so this little gear, okay, that's concentric and fixed to gear B, okay, it's in mesh with this ring R, okay, this ring, okay, but gear B, you have to notice that gear B is not in mesh with ring R, okay, so that's just some important information to keep in mind. All right, and then, all right, so we have this link right here. They're calling it link, okay, DE. So this link right here is rotating about this point here. Okay, so it's rotating like that, and it's causing, okay, this gear C to move upwards. Okay, at the same time, since it is fixed to gear B, it's concentric. They're also, both of them are going to be moving like that. And whatever we have for angular velocity of C, it's going to be the same for the angular velocity of B. Since they're concentric, they're fixed to each other. Okay, so I think now we could start. So to begin with, okay, what we need to do, I'm going to work with gear C. So for gear C, so this is our gear C, okay, and it has that link coming into it. Okay, so this is that link. Okay, and that link, since it's fixed at that point, at point E, right here. Okay, since it's fixed there, and it's rotating. That means we're gonna have a tangential velocity right here, and that's gonna be equal to the omega times the radius. And that's going to be 18 times, let's see, what's this distance? What's the distance, the length of that link? That would be, we have 0.2, which is 200 meters, 200 millimeters, which is 0.2 meters. I'm going to be converting to meters. Okay, so that's 0.2, and then this distance right here, they mention it, it is 300 millimeters, which is 0.3. So add those two, we get a length of 0.5. Okay, and since the omega is 18 and r is 0.5, so that would be 9. So we have a tangential velocity of 9 meters per second. Okay, I'm just going to put a C right here. This is our gear C. Okay, and any other velocities we know that are touching this body. So remember the velocity, this equation you have, let's say we have VB, it is equal to VA plus omega cross product with the r vector going from B to A. Okay, what this means is that, all right, so we have two velocities and we have a body that's rotating. This is just a position vector. So we have a velocity B, okay, let's just call this VB, and we have velocity VA. And what is connecting those two? The angular velocity of that would be in place right here. So what this equation means is that we have two velocities, and then we have a body that's connecting them, and that body that's connecting them is going to have an angular velocity either this way or that way, but it just has an angular velocity. So that's what that equation means, and that we're going to be applying that right here. So the other, okay, so this, I'm going to be considering gear C as the body that's rotating, and this velocity is just one of the two, and then we have to find the second velocity that we already know. And if we take a look, they mentioned that the ring gear, okay, this ring gear R, is fixed in position, and it's touching the body that we're analyzing. That body is gear C, so it's touching that body, okay, and it's going to have a velocity of 0 since it's fixed. So we have now we completed that equation. We have two velocities touching one single body, so that is the 9 meters per second, and then we have a velocity here of 0. Okay, I'm just going to put a velocity right here of 0, and okay, velocity here, another velocity of 0, and that is the body connecting them. And what the important information we want to get out of here is what is the angular velocity. We want to get the angular velocity of that body, because what we're trying to find out is determine the angular velocity of the planet gear and the sun gear. The planet gear is gear B, okay, that's gear B, and the sun gear is gear A. So to find the angular velocity of gear B, you need the best way to go about it, since we have most information about it, is gear C. Find the angular velocity of gear C, and that would just relate to gear B, since they both have the same angular velocity, since they're fixed to each other, they're concentric. Okay, so let's go ahead and complete this equation. So we have V, let's just call this V right here, okay, V1, and this is V2. So V1 is equal to V2 plus the cross product of omega times the position vector that goes from 1 to 2. Oh no, from 2 to 1. Okay, so from 2 to 1. What is V1? V1 is, we called it 9 meters per second, and it's going upwards, so that is a vector of 0, 9, 0. Okay, remember I, J, K is equal to V2, which is just plain 0, that's 0, 0, a 0 vector, okay, plus the cross product, all right, the cross product of omega cross that position vector. And since this, let's zoom in, since we have a velocity right here and it's moving, and this body is rotating, so it's pushing this gear C upwards, then the teeth right here, they're going to be pushing back like that as we move up. Okay, so it could propel it upwards. And because of that, okay, you can see we have like a torque going on, and it's going to spin in this way. And that's a clockwise spin, which means we're going to have a negative angular, we have a negative angular velocity, negative omega. So that is 0, 0, and negative omega. And we're cross-producting it with the position vector, going from 2 to 1. And that would be, okay, since we're going to set our coordinate system like that, the standard, and that position vector, okay, we said, let me choose a different color. So we have, okay, so if we zoom in right here, we said the R vector going from 2 to 1, so from 2 to 1. And that is just the radius. And they mentioned the radius right here, that it's a radius of 0.1 meters. Okay, so that is just negative 0.1, 0, and 0. And once you cross product that, we should get, see, that's 0, comma, okay, so for J, so we have negative J times 0 minus 0.1 omega, like that, and then 0k. Okay, so this is 0i, forget about this comma. So that vector would just end up being, okay, 0, comma, positive 0.1 omega, comma, 0. Okay, so then what we're left with this equation, okay, is equal to 0 plus this vector, so we just forget about this, okay, is equal to 0, comma, 0.1 omega, comma, 0. Okay, so let's just relate the J and the J components. So we have 9 is equal to, so this is the J, and this is J. Remember I, J, and K. So N is equal to 0.1 omega, we divide by both sides, so then we get omega equal to 90 radians per second. Okay, so now we got the angular velocity of the gear C, which is, we said that it has the same angular velocity as B. So omega C equals omega B equals 90 radians per second. All right, so that's the first part. And then the second part is we want to find what is the angular velocity of gear A. So you might be tempted to just say, oh, okay, so if a gear B has a angular velocity of 90 radians per second and its radius is 0.3 meters, you multiply those two, that gives us the tangential velocity, and then that would just translate to gear A, it would have the same tangential velocity, and then you divide by r and solve for omega. But no, that's not how it works. Why? Because the velocity, okay, so the rotation that gear B is going about, okay, it's rotating, is not about its center. It's not about its center. See, in other words, gear C is not rotating about its center. It's rotating about a different point, and that point is the instantaneous center of zero velocity. So when you're looking at, let's say, a wheel of a car or a wheel of a bicycle, okay, and it's in contact, yeah, I drew that bad, and it's in contact with the ground, okay, that rotation, is about a fixed point, 0. Because when you're in motion, okay, when you're in motion like that, uh, the center of that circle does not have a zero velocity instantaneously, right? So the entire thing is in motion that way. Okay, the center has some velocity. But when you look at the place that it's in contact with, and that is going to be the instantaneous center of zero velocity, IC, okay, that at the instantaneous point in time, it has a velocity of 0, and that's what we could relate our motion with. So when we're looking at this gear right here, okay, I'm going to draw gear C right here. So this is gear C, okay, and it's in contact with something fixed, just like the ground, but in this case we have a ring, okay, and that ring has a velocity of 0, and that's why we ended up picking, or this ended up being the IC, okay. Then now we could, so that would be basically like our center. Yeah, instead of having a center of the circle, that would be our new center. All right, and then we could find the tangential velocity. So now that we've found, so the instantaneous center, okay, for gear C would be the same instantaneous center for gear B, since they both have the same angular velocity. Okay, so what we want to find right now is the tangential velocity, okay, of gear B, which is the same tangential velocity of gear A. Okay, but we have to use the instantaneous center of zero velocity. Okay, if we know omega, and we know the position, we know where the IC is, and that IC is right here. So we could use the V tangential is equal to omega times the R vector going from the IC to the point of interest where the tangential velocity is occurring. Okay, so let's just call it P for a point. All right, so omega we know is 90, we solved for it. And then that R vector, okay, is this distance to here, 0.1, plus this distance to here, that's an additional 0.3, which is a total of 0.4. I'm not worrying about signs right now, it's just magnitudes. So that, the tangential velocity would then be 36 meters per second, okay? And then that would be the tangential velocity of gear A, but since it's in mesh with gear, no, that's the tangential velocity of gear B, okay? And since it's in contact with gear A, they both have the same tangential velocity. So the tangential velocity of gear A, okay, VTA, is equal to 36, which is equal to omega, what we want to find, times the R vector going from the center. Okay, here the instantaneous center of zero velocity happens to be the center because it's fixed. It's not translating in motion. Okay, it's not in motion like that. Okay, so then that would be thus basically the R vector is the radius. So the radius is here 0.2. And then once we divide these two on both sides, you plug that into the calculator. 36 divided by 0.2 is 180. Therefore, your omega, okay, no, omega is equal to 180 radians per second, and that omega is omega A. And that's it.